Okay, so let's start with the next talk of the session. It's given by Aditya Bhaskara from Utah about all algorithms for matrix low rank approximation.
Okay, yeah, thanks Arthur, and thanks for inviting me here. So I'm going to talk about online algorithms for low rank matrix approximation problems. Okay, so we all know what low rank approximation is. So these are some very basic problems in analyzing large data sets. So we have, in this talk, we'll consider two problems. So one is PCA or SVD. For the purposes of this talk, I'll treat them both as the same. And usually it is used in applications where you want to do dimension reduction while preserving the signal. Okay, so that's PCA. And column selection is a problem where you want to find a small subset of the columns of a matrix that approximate the full matrix. Okay, so I'm going to define these in a little bit. And so these are not just useful in practice, they're also very nice natural problems in numerical linear algebra. All right, so let me start by defining low rank approximation, or which I'll call also PCA. And the problem is basically you're given a matrix U that you want to approximate, and you're given a small number K, which is much less than the size of than the dimension of the columns. And your goal is to find a k-dimensional subspace of Rd, okay, such that if you project all the columns of U onto that k-dimensional subspace, the error is minimized. Okay. So this is, I'm just setting up notation here. So U will be our matrix, and D will be the dimension of the column. Okay. And there will be n such columns. Okay. And we can also phrase this as the following. So you can say that for every column of U, you want to produce an embedding, which is a vector in a much smaller dimensional space, which is Rk, and I'll call this embedding of Ui as Xi. Okay, and so what you want is that after the embedding, there should exist a recovery matrix, which I will call M, okay, such that U minus Mx is minimized. Okay, so the recovery matrix will basically be a basis for the S that we found in the first definition. Okay, so these two are the same. It's just that this definition turns out to be more useful when I'm defining the online version. Okay, so that's this definition. All right. So for both, and so there's an extensive literature on this, and I'm not going to go too much into this, but I just want to mention that this problem has been studied in lots of settings. There are nearly linear time algorithms in the input sparsity that are known. There are also streaming algorithms for this problem and so on. Okay. So there's a lot of literature, and apologies for just mentioning a couple of them. Okay. So the next problem that I'll consider is column subset selection. So here we are given a matrix U, and now you want to find a space S that is a span of only a small number of the columns of U. Okay. So we want to find k columns of U, such that projecting the columns of U onto the span of the chosen columns results in a small error. Okay. So that's the goal of column subset selection. Instead of an arbitrary subspace S, we just want a span of k columns. Okay, so that's the column subset selection problem, and this has been used a lot for feature selection. That's one of the applications. And there are also many efficient methods for computation. So it started with early works of Friesken and Wimpala, and there are lots of other works here as well. But I mentioned the first work that gave a multiplicative approximation, and some works that followed that also were very interesting. Okay. So, and interestingly, this objective turns out to be closely related to PCA as well. Okay. So, yeah, so we won't need that connection, so I'm not mentioning it. All right, so that's the column subset selection problem. So for both of these problems, we'll be interested in online algorithms for these problems. And what do we mean by this? Right, so we just mean that the points of these columns show up one by one. Okay, and we need to make decisions as soon as these points arrive. Okay, and we'll see what decision means in a little bit. Okay, and of course, as is the case in online algorithms, you always want to compete with the optimum in hindsight, and the ratio of the two measures is called the comparative ratio. So this is the setup. So let's see what we mean by online column selection. Okay, so column selection turns out to be much easier to define in this notion. Okay, so you have a bunch of columns that show up one after the other, and whenever a column arrives, you must either choose to pick it or ignore it. Okay, so that's what you want to do. Okay, so maybe you'll pick the first two, ignore the next two, and so on. Okay, so we either add it to the set that we are building, or we just ignore it. Okay? And your goal is to compete with the best S in hindsight of size k. Yeah.
So there's no assumption on column ordering.
There's no assumption on column ordering. Yeah. So this is all completely worst case. Yeah. And your goal is to compete with the best S in hindsight, and you're allowed to use a little bit more than k columns, but not much more than k. Okay. So we would ideally like S to be roughly k, up to some log factors and so forth. Okay. So that's this problem, and this is in some sense some linear algebra analog of hiring k secretaries. Right? Yeah.
Just when you say log factors, it's log in k, not log g.
Actually, it is log in n. So yeah. So we'll come to the exact guarantee that we can show, but log in k or constant would be great.
Okay, yeah. Trying to get 1 plus epsilon.
Yeah, we're trying to get 1 plus epsilon multiplicative.
It's not probably 1 over epsilon.
Yes, there will also be some 1 by epsilon factors. Yeah.
So you see, compete. What is your objective? You're projecting all the columns onto these.
Onto the chosen ones. Yeah.
The ones that you will choose in the future.
In the future, yes. That's technically the definitional problem. But in what we will show, we'll actually show that even the projection onto the stuff we've chosen so far is small. Yeah, but the objective allows you to use stuff you will choose in the future. Yeah.
But so suppose we just want the best single column, projecting all the directions onto one. Even if the points are Gaussian, the columns are Gaussian, the approximation is going to be really, really bad. Not the approximation of how, I understand, you mean approximation in terms of the best column, but approximation compared to, say, the top principal component would be really bad, right?
Right. Yeah, so we will see that you need certain assumptions, and we will show what assumptions you need in some sense. Yeah, so for exactly the same reason, that it could be very bad. Yeah.
So do you know n?
We assume, I will come to the assumptions we need in a little bit. Yeah. So we assume we know n, and we assume a little bit more than that also. And for the case kind of reasons he mentioned, there are lower bounds that show that you can't do much if you don't assume these kind of things. Okay. So, all right. So let's. So this is the setting for online column selection. Okay. So the online PCA problem, the definition itself is somewhat non-trivial, right? And here's where this embedding view of PCA comes in. Okay, so you get these columns u1, u2, u3, so on. Okay, and what you want to do is, as soon as a column arrives, you want to commit to an embedding xi of the column ui. Okay, so and this xi should be an embedding onto a low-dimensional space. Okay. So as soon as the column arrives, you want to commit to an embedding. Okay, and in the end, you must have this guarantee that you must produce, you must be able to produce some subspace such that these x's can be interpreted as projections onto that subspace. Okay. So in particular, in the end, you want to show there exists some orthogonal matrix M such that u minus mx is small compared to the best approximation error. Okay. So this is kind of a slightly tricky definition, but yeah, this is the one that makes sense for online PC. Yeah.
Or basically you're just, I mean, suppose the dimension was 1.
Yeah.
So then you're basically trying to produce the first singular vector, right? Sort of coordinate by coordinate.
The row singular vector.
The row singular vector.
Yeah. But yeah, I mean, so you can't quite do that, so you need something. Yeah.
So the axis, the property they have to satisfy is that any time the dimension of the span of the axis is at most k. It's something like that.
No, so the x's should actually be short vectors. So they should be, your columns are d-dimensional vectors. Your x's are required to be short vectors.
They have k coordinates.
Yeah. They only have k or a little bit more than k coordinates.
Yeah. So is M larger than, I mean, is it bicriterion? Like M is...
Yeah, so all the results we will show, and actually most of the results that are known for this, they are all bicriteria. So, yeah. So you will have some terms that have epsilon factors, 1 by epsilon factors, and also some log n factors as well.
Okay. You can't show there exists a good k-dimensional space inside of this M.
Actually, that we don't know. Yeah. So yeah, that would be an interesting question to ask. Yeah. Okay. Yeah. So that's the problem here. Yeah.
Sorry, is UK here the best rank K approximation, or is the best subset of K?
Now this is the best rank K approximation. Yeah. So for PCA we compare with PCA, and yeah. And even for column selection, since we are doing bi-criteria anyway, we always compare with the PCA.
Okay.
All right. So this is the setup for online PCA. Okay, so what is known about this problem? So it turns out this problem was defined by Boutsidis, Garber, Karnin, and Ida Liberty in 2015. And what they showed is that you can produce an embedding into k times polylog n dimensional space, which means that each of these x vectors has dimension that is roughly k polylog n. Okay, it will be always bound by that. And you will obtain an additive error of epsilon times the Frobenius norm of the original matrix. Okay. So this is the best known approximation for this. And note that this is actually a much harder model than streaming algorithms for PCA. Right? So because you have to commit to an embedding before you actually see the rest of the matrix. And nothing essentially is known for online CSS, and we will actually see some lower bounds showing that if you don't assume anything, this is very difficult. Okay. So, all right. So the motivating question is: are there efficient multiplicative approximations to both these problems? Okay, because both are pretty natural questions, and so can you get multiplicative approximations to online versions of this? Okay. And what we show is that there's actually a simple variant of what is known as adaptive sampling in this literature, and it gives 1 plus epsilon comparative ratio, and it uses something like k times poly in this, actually log n divided by epsilon columns, if assuming some two conditions. Okay, so the two conditions are the following. So firstly, you must have a rough estimate of what the optimum error is. Okay. In the sense that you want, so by opt I just mean the actual error, like u minus uk, the Frobenius norm. Okay, and we need a fairly rough estimate, but we need some kind of an estimate of this quantity. Okay, so like a poly n factor. Okay, and the second condition you need is that the largest singular value, so the ratio of the largest singular value to this rank k error is at most polynomial. Okay. So there's nothing very important about the polynomial, otherwise logs of those terms will show up in these bounds. Okay. Yeah.
So to understand the first one, does that mean that you were to consider a least variant of that, where you could actually like provide a list where one of them is going to be good in that case?
Yeah, so that's also fine, as long as the number of things that you have is small. That will show up in this bound, okay, as a multiplicative factor. Yeah, yeah.
That was the same question.
Oh, okay. Yeah. All right. So these are two assumptions, and yeah, so we can actually, so we can't quite show that these things are necessary for online PCA, and that's due to a non-trivial reason. So, but for online column selection, you can show that assumptions of this kind are necessary. Okay, so we can show that the number of columns you choose must necessarily depend on these factors. Okay. So that is something. So the other thing about our result is that the algorithm itself is fairly simple, and it's a variant of adaptive sampling, and it's inspired by this really nice algorithm for online clustering, okay, due to Meyerson. Okay, so we'll start by looking at that algorithm. Okay, so this is so let's now consider this online k-means clustering problem. Okay, so this is the usual k-means that we've seen multiple times, right? So and this is the online version of the problem, right? So points arrive, and each time you either add u to s or you ignore u. Okay, so the points u show up one by one. You either add it to your set that you're building, or you ignore it. And in the end, you want two things. You want that the size of the set you end up with is small. It's roughly k. And also, if you compute the k-means objective using s as the centers, you get a value that's almost the same as opt. So this is the natural online version of k-means clustering. And what Meyerson showed is that there is this very simple algorithm that works if we know what the value of the optimum is. Okay? And so the algorithm is simply this. So you see these points one by one, see these points u one by one, and you add u to s with probability that's effectively k times the distance to the things you've seen so far divided by the estimate for the opt that you have. Okay, so in this sense, this is very much like adaptive sampling. So, but it's a one-shot adaptive sampling. It's like an online version of adaptive sampling. Right? You just see one thing at a time. So that's so this is Meyerson's algorithm, and there are many questions here, right? Like firstly, why is the cost small, and secondly, why is the number of columns you choose small? Right? So both of these need to be bounded. Right? And so let me just talk about the cost first. Okay. So for the cost, so the idea to analyze this algorithm is suppose you look at one of the optimal clusters. Okay, so you look at one of the optimal clusters. This is one of the optimal clusters that we started with, and we see what is and these points showed up at some point of time in the algorithm, right? And we see what are the values that of these dus squared that we saw in this process. Okay. And if the sum was more than this c over k, okay, then you can see that these probabilities add up to something more than log n. Okay. And so this means that one of the points from this c has to be chosen. Okay. So this is a slightly hand-wavy proof, but yeah, so this can be made formal. Okay. So one of these points can be chosen, needs to be chosen. Okay. And from that point on, you can argue that the error will be small. Okay. So that's the idea behind this analysis. Okay. And if the sum for the whole cluster was smaller than c over k, then you're in good shape already, because this means that then this cluster doesn't contribute more than c over k to the objective. So there are only k clusters. Okay. So you're still in good shape. So this is a very simple strategy that. So this gives a bound on the objective, and you can use this very similar analysis to also show that you won't pick too many centers. So that's so that's Meyerson's analysis. Okay. And so the cool thing, which is why this whole analysis works, is that the sampling probability is cleanly tied to the objective function, right? To the contribution that a point is making to the objective. Okay, and that's the reason you're able to do this nice analysis. All right. So our motivation was to ask: are there similar clean sampling-based algorithms for problems like PCA and CSS? Okay. So that's one of our questions that we wanted to ask. Okay. So let me describe the setting, at least that I will restrict to during the talk. Okay. So we'll only consider the PCA version. Okay. We won't consider column selection, and we'll always call the input matrix as U. And I'm going to assume, for the sake of the talk, that we know the following quantities, and almost exactly. Okay, so we know the optimum, which is the rank k error for U. Okay, so this I will call it C. Okay, so this plays a very similar role as the C did here. Okay, so you assume that we know this exactly. We also know a bound on the largest singular value, which is sigma max of U. Okay, so these are two assumptions that I will make for the sake of the talk. All right, so now let's try to proceed try to explain how this algorithm will work. Okay, so the framework is, as I described before, you get these columns, and you want, whenever a column comes, you want to output its embedding. Okay. So what we will do is, we'll always maintain a subspace S. Okay, so in clustering there was always a set of points S we were maintaining. Now we maintain a subspace. Okay, so I want to define an analogous algorithm here. Okay. So now we'll maintain a subspace S. And every time a point comes, you will pick a basis, or rather you will always have one fixed basis for this S, and you will embed this point ui into that subspace. Okay. So this will give an embedding of dimension which is equal to dimension of S. Okay. But we'll have some kind of an upper bound which we call R. Okay. So this is the maximum number that we will output, and you will pad zeros so that you always output an R dimensional vector. Okay. So this is the framework that we are considering. That each time you get a vector, you embed onto the S that you have so far, you add some zeros so as to make sure you always output the same dimension. Okay. So this, yeah, right. So the whole point is how do you pick this S? And so an ideal algorithm, if you want to be inspired by Meyerson completely, would be to do something like this, right? So you know opt exactly, so you can say that every time a column shows up, you add it to this subspace, and you take the span of the original space plus this column, and you do that with probability which is proportional to k times the projection that UI had orthogonal to the subspace so far, divided by this this number xc. Okay, so this is a very natural choice of to do this, and let's call this number pi. Okay, so this is for the column UI. This is the probability of adding. Pi depends on what S we had so far. All right, and note that this is very, for those of you who know of adaptive sampling for PCA and so forth, this is like a one-pass adaptive sampling. Right? It just picks one after. And so one thing that is true is that if this algorithm always, if you are able to prove good guarantees for this very simple algorithm, you actually get online algorithms for both PCA and column selection, because you're actually choosing some columns and adding them to S each time. All right, but it turns out this simple algorithm we actually don't know how to analyze. Okay, so we believe that this also gives a good approximation, but we don't know how to analyze this. Okay. But it turns out that there are still things from this algorithm, there are still parts of it that we can analyze. Okay, so one simple claim, which turns out to be useful later on, is if you do this process, the number of large PIs is small. Okay, so what do I mean by large? So specifically, we want to claim that the number of indices I for which pi equals 1, remember pi was defined as this quantity, for which pi will be equal to 1 is small. I will say what small means here. So, and the reason for this is that if you have such a thing, then every such UI, firstly it will always be chosen because pi will be 1, right? And every such UI has a large component orthogonal to the previous ones. Yeah.
What is small? Pi is small or the vector? What is small? Pi.
Sorry. Yeah. No. So the number of I for which pi equals 1 is small. So, okay. So the number of such indices is small.
Oh.
Okay. Yeah. The size of the set that you pick. Okay. So. All right. And and the way we try to show this is by saying that if you have a bunch of PIs that are all 1, then it means that each corresponding UI has a large component orthogonal to all the previous vectors.
Previous chosen ones or previous ones also? Previous
chosen ones.
Okay.
Yeah. So previous ones that also had this property is what I will use. Okay. Yeah. So this is this is the guarantee that we have. And we want to show that this kind of a thing is impossible, and for this there's a very simple geometric lemma that you can write. Okay, so if you have a bunch of vectors u1 through ur, okay, so it's a sequence of vectors such that for every I, the projection of ui orthogonal to all the vectors that preceded it. Okay, I'm just introducing some notation here. It's called pi sub I minus 1. So if assume that number is at least gamma, so if you have this kind of a guarantee, okay, then you have many singular values. In particular, you have something like r divided by roughly log n singular values of this matrix of u that are at least gamma by 2. Okay, so you have a matrix with a bunch of columns. Every column has at least a gamma component orthogonal to the span of the previous guys. We are saying that this matrix has at least r by log n columns that are at least r by log n singular values that are at least gamma by 2. Okay. So this is an ordered version of what is called this leave one out distance. Okay, so for those of you who know, and there you don't actually look at the component orthogonal to the previous one, you look at the component orthogonal to everybody else. Okay, and there you can actually get that r by 2 singular values are large. Okay, you don't lose this log n. Okay, but here it turns out you have to lose this log n. All right, so but this is the lemma. All right, and for now let's pretend that this number is log n. Okay, so why is this relevant to us, right? So we wanted to show that having many large PIs is impossible, right? Many PIs that are 1 is impossible. And now let's suppose that you had r of these PIs that were all 1. Okay, then what this lemma tells us is that if you just restrict the matrix to these columns, to the columns you've chosen, then you have 10k log n, r being at least 10k log n. So if you divide by log n, so if you use this lemma, it tells you that r by log n singular values are all large. And so you get that u has at least 10k singular values that are at least this c divided by 4k. Okay? And this is a contradiction because the rank k error is only c, right? Because so you can't have too many large singular values. You can't have something like 10k singular values that are more than c by 4k. Okay? So this is the way to bound this r. Okay? So what we've shown is that having a large number of PIs is impossible. So a quick note, so the lemma is actually pretty easy to show. Okay, so it basically follows from just two views of the volume of the simplex defined by these UIs. We know that every UI has a good component orthogonal to the previous ones. So if you just use the base times height formula for the volume and you use it inductively, you get that the volume is at least gamma to the r. Okay? And then you use the fact that the volume is also the product of singular values, and this is why this sigma max comes into the picture. Okay? So you kind of have one big singular value that's contributing all the volume. Okay? So this is roughly the proof of this lemma. Okay. All right, so that's what we can show, right? Like having many large PIs is not possible. Okay. So before we move on, I want to mention one brief issue with the case of small PIs. Right? So we said large PIs is okay, right? And PI is defined like this. And the problem, which is the reason we can't analyze this algorithm fully, is that in some sense, if you have a bunch of columns that have small PIs, right? We don't sample them, but we don't have any memory of what those columns were, right? Because if you don't sample them, you kind of lose track of all information about these columns. Okay? So in some sense, we don't see anything of them, and you can think of some potential-based analogs of what we saw before, but turns out that they don't work either. The only fix we know is using a slight variant of this algorithm. Okay. Yeah.
If you maintain the distribution of PI values, will that help you in some way? So
what do you mean?
You know that things are going bad.
Right. So I don't think the values themselves help. Yeah. I think the vectors are also important. Right. Like you could have, I guess the two examples is you had many vectors that were all aligned the same way, all having small PI, versus many vectors that were all very different and all had same PI. You need some way of
maintain some space or
differentiating between them. Okay. So the algorithm we propose is in some sense, so it's an algorithm that proceeds in phases. Okay, and the way it does it is you have for now assume that all the PIs are less than 1, okay, just for simplicity. Okay, so what you do is you divide these vectors into phases, such that in every phase the p's add up to 1. Okay, so and after every phase we add one direction to this space S that we are maintaining. Okay, so this is how the algorithm proceeds, and this vector W that's added is in some sense a summary of all the vectors in that phase. Okay, so this is the idea behind this algorithm. And all right, so And so initially you start with S equals phi, and these are a bunch of columns whose p's add up to 1, and at this point you add one vector, okay, and you keep going. So this is the algorithm. So what is and the intuition is that in some sense you are adding roughly one vector when even the previous algorithm would have added one vector, but you are adding a much better vector in some sense. Okay, so you have a summary of everything that happened in that phase. Okay. So yeah, so quickly let's see what the summary of a vector is, right? So a summary of a phase is, right? So if you have a phase that consists of u1, u2 up to ut, we do a very simple summary, which is basically the random linear combination of the ui's. So this is the vector that we will add at the end of each phase. Okay. And what is and these signs are chosen uniformly at random.
So in the phase you have some memory then?
You just have a memory of this one vector. Okay. So yeah, so you keep track of one vector that you will keep adding in this phase. Okay. Yeah, so that's the reason it's not much memory. Yeah. So right. So and the reason we do this is because, firstly, I mean, you can see that the expected length of this vector is just the sum of squares of these lengths. Right? So this is easy to see. But more importantly, for any projection pi, because projections are linear, you have that the expected length of the projection of W is the sum of these square lengths of the projections. Okay. And this is nice because it gives us two things. Okay, so the first thing is, if you look at the projection orthogonal to S, where S was the S at the beginning of the phase, okay, then with a good probability you have that the projection of this W orthogonal to this S is roughly the projection, sum of the projection squares of all these individual vectors in that phase. Okay. So this just is because of this fact that I said before, right? So the expectation is the same. Some basic concentration bound gives something like this. Okay. Okay. And the other thing, which is actually a slightly tricky thing, is that if you consider the projection orthogonal to the optimal PCA space for the entire matrix. Okay. Note that we have no idea what the space is, but just for the sake of analysis, let's consider pi k to be the optimal k PCA subspace for the entire matrix. Okay. Then you have that even this kind of a bound holds, right? So the projection of W is not much more than the sum of projections of all these other vectors. Okay. So let's see how these two bounds are useful. Okay. So I want to say that these two bounds immediately imply that the number of phases is small. Okay. So one thing to note is that these bounds don't always hold. They hold with reasonable probability, but the probability is more than some constant, because this one holds with 3/4, this one also holds with some 3/4 probability. So let's assume all phases are successful, and I want to show that the number of such phases is small. Okay. And so the reason is the following. Okay, so by the first part of the bound, we can show that every phase has a large projection, or the W at the end of each phase has a large projection orthogonal to all to the S so far, just orthogonal to all the W's added so far. Okay. And this is nice because this allows us to use this geometric lemma that we define. Okay. So it says that if your number of R's is more than k log n, then what it shows is that the matrix W has a rank k error of at least this C. Okay. So we are not done yet, right? Because this is some new matrix W. All we showed is that it has a large rank k error. Okay. But now this is where the second part comes in, right? So the second part shows that if you took the optimal k-PCA subspace of the entire matrix, the rank k error of the W's you're adding was only smaller than this, and these we know add up to exactly C, because that was the definition of the rank k error for the whole matrix. Okay. So that's the reason. So that contradicts this too. Okay. So this is why you can't have more than something like k log n columns, k log n phases. So all right. So this is basically the proof. And so this is the proof that you won't add too many, that the space won't get too large. Okay? So now why is the error small? This is also very simple. Note how the PIs were defined, right? So they were basically this min of 1 and this. Okay? And and these PIs in a phase were always adding up to 1, which meant that these numbers were adding up to 1. Okay? So which means that the error, which is this term, in every phase is at most something like 4k by 4 times c by k. Okay, and this is again, note the similarity with this Meyerson's analysis, right? So it's basically it's like one cluster. Okay. And yeah, so over all the phases we have that the sum of these projection errors is therefore at most something like log n times this c. Okay, because the number of phases was 100k log n. So that's the bound we have, and so the S you have in the end has a log n comparative ratio. So that's the argument so far. Okay, so this is good, but we have a log n factor here, but it's a multiplicative factor. Okay. All right. So how do we now get to 1 plus epsilon factor? Okay. So the first thing to ask is, what if you're allowed 2 passes over the data? Okay. So the same data, same order, you get 2 passes. So now it's somewhat easy to see. Right, so you can use our algorithm to obtain the space S. Okay. And now you can use one of these additive approximations that were known before, and you can feed the leftover vectors to this additive approximation. Okay, so by leftover I just mean the parts that were not covered by the span of S. Okay. And you can feed those vectors to the additive approximation, and then overall you get a multiplicative factor. So this gives a 1 plus epsilon comparative ratio, and just to be sure, the embedding will be the concatenation of the 2 embeddings. Yeah.
Your subspace S is like this inner product of these vectors with random signs, right? So
it's the span of such vectors.
Yeah. So most of these vectors will be left over, right?
Oh no. So sorry. What I mean by leftover here is the part of the component of these UIs that are orthogonal to the S so far. Okay. That are orthogonal to the S.
And then you first project it onto the orthogonal component, and then.
Yeah. Just feed. Yeah. So we are getting 2 passes, right? So in the second pass, whenever you see a vector, you project it to the. You take the component orthogonal to the S you obtained in the first part, and you feed that in to this additive approximation algorithm. Okay? And we use this as a black box at this point. Yeah. All right, and this gives a 1 plus epsilon comparative ratio. And so it turns out, if you think about it for a second, you can actually do these 2 passes in just 1 pass. Okay? And the reason is, you can imagine doing the algorithm that we've been doing. Okay, so you get these columns, and you come up with these different S's, but in parallel, suppose you send the projection orthogonal to the S so far to a copy of this additive approximation algorithm that we are sending, that was there in this work, right? So you just send the orthogonal component to to this black box. Okay, of the projection so far. And you just you need to now output an embedding, and you output the concatenation of the 2 embeddings. Okay, so whatever the embedding we got plus whatever embedding these guys get. And it turns out that because we have a bound not just on the projection in the end, but on a projection sum of these kind of terms at every step. This is roughly what Robbie was asking earlier, that our guarantee actually gives a bound over the running sum. Okay, that is at most some log n factor of the opt. So this is the reason you can do this 2 passes in just a single pass. And it turns out that this gives a 1 plus epsilon comparative ratio for online PC. So how long do we have time on that?
You are approximately done.
Okay. So I will be done. I'm almost done. Okay. So all right. So yeah. So one thing you could ask is this? One thing we can show is that the same kind of result is also possible for column selection. The only trick there is how do we avoid keeping track of the sketch of a phase, right? Here it was important that we had this vector w that was a sketch of a phase. But it turns out if you sample only like log n things in every phase, then this actually still works out. Okay. So, and the other thing I wanted to talk about is the importance of knowing or guessing the optimum. Yeah.
How does this whole thing compare to like online ridge lever score?
Oh yeah. So I actually So it. So we don't think that this that kind of reasoning gives some bound on the rank k error. Okay, so it gives a bound, or if you want to approximate the whole matrix, but we don't know if it gives a bound for the rank k error.
Oh,
yeah, but maybe we can talk about it.
Set the probabilities. But I mean,
we don't know the PCA, right? So we don't. How do you?
Well, you don't know how to set the regularization or the.
Yeah, we can talk about this offline, I guess. Yeah. So that's a good question. Yeah, we also were not. Yeah, but to the best of our knowledge, we don't know how to make that kind of machinery work. Yeah. Okay. So, all right. So what is? So one thing I want to comment about is the importance of knowing or guessing the optimum. And I wanted to, just say maybe this is the kind of examples you had in mind. But for problems like column selection, if you have a basic some lower bound L and some upper bound U, any constant comparative algorithm must pick at least some log of U by L columns. Okay, and this is why we have these assumptions that these ratios are bounded by polynomial. And the reason is that you can just have completely orthogonal vectors show up of like very different lengths, and the online algorithm doesn't know if these vectors lengths keep growing or if they'll just stay the same. So in some sense we don't have a way of getting around this kind of a bound. Okay. This is for column selection. Okay. But for PCA you can do something interesting. Okay, so remember in PCA, if your vectors keep growing a lot in length, then you can start reusing the coordinates in the embedding. Okay, so this is, I won't go into the details, but this turns out to be, it's a weird thing that is possible for PCA. Okay, so it might be that for PCA you can actually get an algorithm without any such assumptions. Okay. So, alright, so let me end there. Okay, so there are a bunch of questions that came up during the talk. So the first thing is that this one pass adaptive sampling, the very basic algorithm inspired by Meyerson, does it itself work? So this we don't quite know. Okay. And so the other thing is, are there algorithms without any dependence on these condition number parameters? Right. So at least for the case of PCA. And the other thing is avoiding the knowledge of opt. So all these are natural open questions, and of course there are lots of open questions when we go to this. How about other norms in terms of approximation, right? But for spectral norm, I mean all bets are off, because even for column selection I don't quite know how to do this. So all right, so and you could ask various other errors as well. All right.
Any questions? Okay, there were many questions during this. Oh, but still.
Your question was about depends on the condition number for PCA?
Yeah. So actually for both of these things, we also have a log dependence on this, not quite the condition number, but this ratio between the sigma max and the rank k error. Okay. And that, we don't know if there are like reasonable algorithms that can avoid that.
That's not necessary for similar reasons that you said of like.
So we're not entirely sure, at least not for PCA. For column selection, I think these kind of low bounds can be shown, but for PCA, it's unclear if we can show such low bounds. Yeah. Because essentially you have the power to reuse. You can fix an embedding and later claim that that was not the projection I had in mind. There's a different projection that still works. Right? So you can play such things with.
Any more questions? Okay, if not, let's thank the speaker again. And we have coffee break until I think